Hello friends, welcome to the next lecture on convective heat transfer. In today's class, we will actually be looking at one of the more modern technologies or techniques for solving the equations of convective heat transfer, namely the computational fluid dynamics. So what do we understand by computational fluid dynamics? In computational fluid dynamics, we solve all the governing equations, the governing partial differential equations of conservation of mass, momentum and energy, and wherever required species and various other equations as coupled partial differential equations which have to be solved numerically, and therefore they are discretized. So you create a grid of control volumes which basically are obtained by subdividing your region of interest, what we call as a computational domain, into discrete control volumes or grid point control volumes, and you integrate the partial differential equation over these discrete control volumes in order to get algebraic equations, simultaneous algebraic equations for the values of the various flow field variables such as the density, the velocities in x, y, z directions, temperature, pressure and various other flow field variables as a function of x, y, z and t. So suppose let us imagine we have a rectangular computational domain and we divide it using, let's say, vertical and horizontal lines into various grid points. At each of these grid points, I would need to evaluate the values of u, v, etc. And these values will be actually evaluated in terms of the neighborhood values. So if I have a control volume here and you have 4 neighboring control volumes to the left, right and top and bottom of that. Now the value of the variable at this location will be affected by the values of the variables in the neighboring control volumes, and therefore you get what you call a simultaneous algebraic equation in the values of the variables at all the grid points. So you get a system of equations in the form of a matrix equation. You solve this equation and obtain the values of the various flow field variables in all the grid points in the computational domain. Now once they are available, then using them you can actually find out the differential or the derivative to find out the wall heat flux or the wall friction coefficient, or integrate them to find out the mass flow rate, the momentum flow rate, the fluxes, the forces, and those quantities. So this is the fundamental summary of the techniques of CFD. And today, because it's used so widely, there is a large number of computer programs which have been developed over decades, and they are available for ready use by people both in the academics and in industry. Okay. So what I will do today is to give you a brief introduction to the fundamentals of computational fluid dynamics. We will restrict ourselves in convective heat transfer to incompressible flows, steady flows, and since we are dealing with now boundary layers, let me also restrict myself to 2 dimensions so that the understanding of the techniques of CFD become slightly easier. And then we will show a demonstration of the results that we obtained using ANSYS Fluent, which is one of the CFD software for laminar flat plate boundary layers of air and water for certain conditions. Okay. So that is the objective of today's lecture. So let's move on to the whiteboard and understand the techniques of CFD. Okay. Okay. Now, okay, computational fluid dynamics or CFD. So it's very important for any student of convective heat transfer to understand computational fluid dynamics from fundamentally, without which it simply becomes what is called a colorful fluid dynamics, CFD again, but without any physical understanding. It just becomes a bunch of colors, but no physical meaning in it, right? So let's not work with colorful fluid dynamics, let's work with computational fluid dynamics. So in computational fluid dynamics, we typically deal with the conservation equations of mass, momentum and energy. So let me write down the equations. Continuity equation. So for now I will write for 2D steady and constant properties. Okay, so I'll be writing down the two-dimensional steady-state equation at constant properties. So what you will get is an incompressible, of course. Okay, so this will be del u by del x plus del v by del y equal to 0. So this is your first equation, that is your continuity equation. The momentum, x momentum, you'll get u del u by del x plus v del u by del y is equal to nu times del squared u by del x squared plus del squared u by del y squared minus 1 by rho del p by del x. Similarly, v momentum or y momentum equation will look u del v by del x plus v del v by del y is equal to nu times del squared v by del x squared plus del squared v by del y squared minus 1 by rho del p by del y. And energy equation, can write in the same form, u del t by del x plus v del t by del y is equal to alpha del squared t by del x squared plus del squared t by del y squared. So you see that the equations all look quite similar to each other. Okay, the minor changes that come because of mu getting replaced by alpha here, and there is a pressure term here which is not present here, and so on. But otherwise, if I replace, for example, this u with v, I get this equation, this v with t, I get this equation on the left hand side as well as the right hand side without this one term which is there. So the equations look quite similar to each other. Now let us carefully look at these equations. If you look at these equations, the unknowns or the dependent variables that are there here are rho, u, v and p. Okay, so you have rho, u, v and p, density, velocity, x velocity, y velocity, pressure and temperature. There are 5 equations and there are 5 unknowns and there are 4 equations. Okay, so since density is usually taken to be a constant, okay, or density is taken to be a function only of temperature, this can be evaluated directly. So you get u, v, p, t, and you have 4 equations, 4 unknowns and 4 equations. Okay, 1, 2, 3 and 4. So that looks fine, but then there is a problem. What is the problem? The problem is that the value of pressure is required in order to solve the momentum equation correctly, but then there is no equation for pressure. Okay, the equation of state is not used in the incompressible flows, and even if it is used, it does not give you any extra information, because in incompressible flows you treat the density variation with respect to pressure as negligible, so you cannot use the equation of state in that form. So this pressure comes out to be a problem. Okay, so how do we evaluate this pressure? I can, let us say, evaluate u from this equation and v from this equation. Then the only equation that is left behind is this, and that does not have any p. So how do I calculate pressure? Okay. So now, in order to solve this problem, people thought of two alternatives. One alternative is to eliminate pressure using this, so that these two give rise to an equation which is devoid of the pressure. Okay, so that is one approach. So let us call these as equations number 2, equation number 3, and equation number 4. So people were thinking of a method by which you can use equation 1 in order to eliminate pressure between equations 2 and 3, so that the pressure does not become a hindrance in solving the equation. It can be removed by elimination. So this is one approach, and in that process you transform these equations in terms of two other flow field variables called the stream function and vorticity. So one approach is the stream function vorticity approach, by which you eliminate pressure between these two equations using the continuity equation. The second approach is to guess some value of pressure and solve the momentum equations. But now you know that these momentum equations will not satisfy the continuity equation because the pressure that you have given is not a correct value. So somehow you substitute the velocities into this in order to obtain a correction for the continuity in terms of the pressure. Okay, so in some sense you substitute for the velocities here and here in terms of this equation and this equation, so that this gives rise to an equation in pressure, and you solve that equation for pressure, so that you get the pressure that satisfies the continuity equation, which can again be substituted back into this equation. So that sort of methods, or that kind of methods, are called the pressure correction methods. Okay, so you get two different categories of methods in incompressible flows. One is stream function vorticity. So in this, pressure is eliminated from equations 2 and 3 using equation 1. Okay, and the second approach is pressure correction approach. And this P is solved for using 1 and used in 1, 3. Okay, so both of these are actually applicable for incompressible flows. Where density is not a function of pressure. Okay, so this is the thing. When density is a function of pressure, of course, the equation of state comes into picture. And so for compressible flows, you solve 6 equations and 6 unknowns. The 6th equation being 5 equations and 5 unknowns. The 5th equation being the equation of state. Okay, so in the case of incompressible flows, you have to use one of these two approaches. Okay, so now let's start with the stream function vorticity method. So stream function, we have already defined psi in your equation of similarity method, is defined such that del psi by del y is v, del psi by del y is u, okay, and del psi by del x is minus v. Okay, so when I define it like this, then it automatically satisfies continuity equation. Why? Because continuity equation is del u by del x plus del v by del y is 0. Del u by del x is del squared psi by del x del y, and del v by del y is del squared psi by minus del squared psi by del y del x, and therefore just adding the two gives you 0. So the continuity equation is automatically satisfied if I get a stream function such that you get u is equal to del psi by del y and v is equal to minus del psi by del x. Okay, so then you define vorticity. Vorticity in fluid mechanics is defined as omega vector, it's a vector, is del cross v. Okay, so this has the vorticity in three components. Let's say omega x into I plus omega y into j plus omega z into k. Now each of these is the direction normal to the plane on which this vorticity is operating. So in a two-dimensional case, this I and j are in directions which are not relevant. K is the vector normal to the xy plane, which is the plane of our interest, and therefore in 2D, omega x equal to omega y equal to 0, and this happens because del by del z of anything is 0, and we also have w, which is the velocity component in the z direction, which is also 0, because of which in 2D you get omega x is equal to omega y equal to 0, and omega z turns out to be, this is equal to omega, which is the number modulus of this, of the magnitude of the vector, and that is equal to del u by del y minus del v by del x. Okay, so you can do that by doing this. This is an operator I del by del x plus j del by del y plus k del by del z, and this is ui plus vj plus wk, and in this w is 0. So you can actually take the cross product and verify that you will get the omega x and omega y to be 0 and omega z to be equal to this. Right? So this is the expression. So now this I can substitute in terms of the stream function. This becomes del u by del y, which is del squared psi by del y square, and minus del v by del x, which will be plus del squared psi by del x square. So you get del squared psi by del x square plus del squared psi by del y square is equal to omega. Okay. So okay. So actually it will come the other way around. It will be del v by del x minus del v by del y. So you will get a negative sign of the omega. So what I'll get is del v by del x minus del u by del y equal to omega, and that is equal to minus del squared psi by del x square plus also del squared psi by del y square. So you get an equation del squared psi by del x square plus del squared psi by del y square equal to minus omega. Okay, so this is, let us say, equation number 5. Now, if I substitute these, the del psi by del x equal to del psi by del y equal to u and del psi by del x equal to minus v, and using them in the two momentum equations. Okay, so what I do is I take the second equation and differentiate with respect to, so you need to get a del u by del y, so you differentiate this with respect to y, and you need a del v by del x, so you differentiate this with respect to x, and then subtract the second from the third. So what do? You do del 2, del 3 by del x minus del 2 by del y. This is basically what you do. So basically this is a v equation, you differentiate with respect to x, and u equation differentiate with respect to y in order to get an equation in terms of omega. So what do you get? The second, the third equation is del by del x of v del u by del x. So it is, u del v by del x. So it is del u by del x into del v by del x plus u del squared v by del x square. Okay, so this is del by del x of u del v by del x. Okay, so the next term is v del v by del y, so it becomes del v by del x into del v by del y plus v del squared v by del x del y. Okay, minus, let us do the left hand side of equation number 2, so which is del by del y of, so I'll keep this in the bracket, del by del y of u del u by del x, so it will be del u by del x into del u by del x plus u del squared u by del y del x. Okay, so del u by del y into del u by del x. Okay, this is differentiated with respect to y. So del u by del y into del u by del x and u del squared u by del y del x plus v del u by del y. So del v by del y into del u by del y plus v del squared u by del y squared. Okay, so this is the left hand side of the other equation. This is equal to the viscous term is del squared by del x squared and del squared by del y squared. So if I'll just take del squared by del x squared of del, the differential order can be changed, so it will be del u by del x plus del squared by del, this is the third equation number 3 that I am doing. So it will be del v by del x and del squared by del y squared of del v by del x. Okay, so this is equation number 3, right hand side with respect to x, minus, so this will be with a nu here. Okay, it's already nu here, del squared by del x squared of del u by del y plus del squared by del y squared of del u by del y. Okay, and then the pressure term will be minus 1 by rho, which will remain as it is because density is a constant. I'll get a del squared P by del x del y minus del squared P by del y del x. And this is basically what we are trying to seek to do, eliminate the pressure by cross derivatives. So this gets eliminated because del squared by del x del y is the same as del squared by del y del x. We have eliminated the pressure. And on the right hand side, you get del squared by del x squared of del v by del x minus del u by del y. And similarly, del squared by del y squared of del v by del x minus del u by del y. So you get del square omega by del x squared plus del square omega by del y squared on the right hand side. And on the left hand side, what do you get? You get some terms which can be combined. Say, for example, del v by del x. There is one term here with del v by del x. There is another term here del v by del x. So del v by del x multiplied by del u by del x plus del v by del y. So that's continuity equation says del u by del x plus del v by del y is 0. So this and this together become 0. And similarly, there is a del u by del y multiplied by del u by del y multiplied by del u by del x plus del v by del y. So this term and this term together go to 0. So this and this go to 0 by continuity, and this go to 0 by continuity, because it is del v by del x multiplied by the continuity equation del u by del x plus del v by del y, which is 0. And here it is del u by del y multiplied by del u by del x plus del v by del y, which is 0. So if I remove those, then I get u multiplied by del square v by del x square and del square u by del y del x. So if I take the u del by del x as common, then I get a del v by del x minus del u by del y, which is u del omega by del x. Similarly, here you get v del by del y as common. There is a del v by del x minus del u by del y, which is v del omega by del y. So if I combine those and write, then you get u del omega by del x plus v del omega by del y is equal to nu times del square omega by del x square plus del square omega by del y square. This is equation number 6. Okay, so now instead of equations 1, 2 and 3, we have equations 5 and 6 which you have to solve. So you solve equation 6 to get omega, and put that value of omega here and solve equation 5 to get psi, and once psi is available, then you can get u and v, and those things can be used again here for this. So this can be written as del psi by del y and minus del psi by del x, and the whole thing can be solved. So this u and v can be obtained from psi, and you can solve this. So by solving equations 5 and 6 simultaneously at all the grid points of the domain, you get the solution for psi and omega, and from psi and omega you can actually evaluate u and v. And once that is done, then you go to the energy equation. Using the energy equation, you can solve for temperature. So you can, once the u and v are known, then this equation can easily be solved. So you get the temperature. Okay. So how those equations are solved, I will not go into too much detail at this point. I will go into a little bit of detail of that in discussing about the pressure correction methods, because there in order to understand what is required to be done, we need to do a little bit of that solution process. So we'll do that. But as of now, in the stream function vorticity method, we will just leave it like this, saying that we are going to solve equation number, so you guess a value of psi, and using that value of psi, you calculate u and v and solve this equation. You get a value of omega, put those values of omega into this and get the values of psi, and you are differentiating the values of psi, again you get u and v. So simultaneously solve and iterate. Okay, so that is the process that you will do. So let me just write that method. So first, guess psi of x comma y at all x, y in the domain. Then evaluate u is equal to del psi by del y and v is equal to minus del psi by del x in whole domain. Then go to solve equation 6 to obtain omega in the whole domain. Okay, then using these omega, solve equation 5 to get psi. Okay, so initially you guessed psi, so in the first step. So once you have gotten the updated value of psi from the new values of omega, then go back to step 2 until psi and omega don't change with it. Okay, so this is your stream function vorticity method. So you got the equations and you got the method for solution, and you'll be solving that using that. So this is one. In most commercial software, this is not a method that is used. This is an older method which is still in vogue in some codes and some parts, but by and large, this method has now been replaced by the pressure correction kind of methods. So we'll talk about the pressure correction methods. The pressure correction methods are also called the primitive variables method. Since in the pressure correction methods, you directly solve for U, V, P, etc., and not for derived variables like psi and omega. Okay, so since you are solving for primitive variables, it's called a primitive variables method as well. Okay, so this is the name for the second class of methods. Okay, so the first class of methods we called as a stream function vorticity method. Okay, and now the second class of methods is a primitive variables method. What is the primitive variables method? You actually solve for U, V, and P. So how do you do that? So if you go back to the equation that we wrote, 1, 2, 3. Now, in order to solve this equation, we need the value of pressure. Okay, in order to solve this equation, you need the value of pressure. So what we do is to guess the values of pressure. In any case, the equations are coupled, and therefore, in order to solve this equation, suppose this is an equation in U, I need the value of V, and this is an equation V, then I need the value of U. So I have to guess all the variables. So I guess pressure. Let's say P star is the guessed value of pressure. I guess U star, which is the guessed value of U, and V star, which is the guessed value of V. Then I use this equation and solve for the new value of U star. Okay. And I do use this equation and solve for the new value of V star. Now we know that when I solve for the U star here, the pressure is not correct and the V is not correct. So the solution of equation 2, U star will not be equal to U. It will be different from the U at every point. Similarly, the solution of this equation, which contains V star, we use the value of U star, which is not exactly U, and we use the value of P star, which is not exactly P, and therefore the solution of this V star will not be equal to V. There needs to be a change or correction that needs to be done. So using these two, I substitute into the continuity equation saying that U is equal to U star plus U prime and V is equal to V star plus V prime. And since the U star equation with P star satisfies the momentum equation and V star equation with P star satisfies the momentum equation, I eliminate that and get an equation for pressure corrections in terms of the continuity equation. Once the pressure correction is solved for from the continuity equation, the P prime, if I say pressure P is equal to P star plus P prime, which is the pressure correction, I solve for P prime from this equation, and once the P prime is obtained, I correct pressure to get the P updated value of pressure. And since the pressure correction and the velocity corrections are linked in deriving this equation, you can calculate the velocity corrections also and correct U star is equal to U star plus U prime equal to U and V star plus V prime equal to V. So this will be the new value of U star, U prime and P star, because you have to now go by iteration and solve again. Now, because we are solving three equations and we are substituting from one in a sequence, the continuity may not be completely correctly satisfied. So you keep iterating this. So you solve for u star from here, v star from here, and then substitute both of these into this to solve for p prime, and get p prime and correct p, get u prime, v prime and correct u and v, and then put them back into the momentum equations and continue the iteration until such time that u prime, v prime and p prime actually vanish, because no more correction must be required if the equations are correctly satisfied. So the values of u prime, v prime and p prime should identically or should actually vanish, or which should become extremely small values for the convergence. So this is basically what we understand by the primitive variables method. So let me just write that down and then we can go. Okay, it's the wrong place to insert the page. Okay, so I'll set a page here. So I'll just write down the first step is guess u star, v star and p star as initial guesses of u, v and p. Now solve equation 2 to update u star, and equation 3 to update p star. Okay, then using continuity equation, and using u is equal to u star plus u prime, v is equal to v star plus v prime, and p is equal to p star plus p prime, get an equation for p prime. Okay, so the p prime equations derived from the continuity equation. I'll just show you how that is done, and then solve for p prime. Hence, get u prime and v prime. Then correct p is equal to p star plus p prime, u is equal to u star plus u prime, and v is equal to v star plus v prime, and use these as initial values, initial guesses, and return to step 2. Continue iterations until u prime, v prime and p prime become small or negligible. That is, the changes in u, v and p that we do here, they should become negligibly small. So then that we take it as converged. Once this is converged, then you can go for solve equation 4 for temperature. Okay, so this is the method that we use in primitive variables method. So just let us go and see how the equations are solved. The method that I'm going to describe now would be actually generic and common to both primitive variables method and to the stream function vorticity method. So So let's understand that. So what I'm going to do is to look at these equations. Look at these equations, and we said that these equations look quite similar to each other. Okay, and when we derive the vorticity equation, the vorticity equation also looks quite similar to that. Right? The equation number 6 also looks quite similar to that. So the method that I'll be using for solving these equations, I'll just can do the discrete equation integration over a control volume, so that the problem you understand how the equations actually are solved. So let's write this equation in the form of u del phi by del x plus v del phi by del y is equal to sum gamma times del squared phi by del x squared plus del squared phi by del y squared. Okay, so this is actually, let me write this as gamma by rho into this plus some source term, let's say S phi. Okay, so if I look at the various equations that I wrote just now, let's say the equation for this. So if I substitute phi with u, I get this equation, u del phi by del x plus v del phi by del y. This nu is mu by rho, so mu is the gamma. Okay, del squared phi by del x squared plus del squared phi by del x squared, and this is the S phi term for u. Similarly, u del phi by del x plus v del phi by del y, phi is v here, and so nu is mu by rho, so this is gamma is mu, and del squared phi by del x squared plus del squared phi by del y squared plus source term for that. Similarly here, u del phi by del x plus v del phi by del y, phi is t here, is this k by rho Cp. So k by Cp can be the gamma. So then you have del squared t by del x squared, del squared phi by del x squared plus del squared phi by del y squared. The source term is 0. And in the same fashion here, u del phi by del x plus v del phi by del y, phi is omega, and the nu is mu by rho, so mu is the gamma, del squared phi by del x squared plus del squared phi by del y squared, and the source term is 0. Okay, so the equation that I have written here, generic equation, is the general form of all of the transport equations to be solved. So I'll write it in this fashion. So now on the left hand side, I would bring this rho here. Okay, so what will happen? This rho, if I bring it to the left hand side, rho u and rho v. Okay, so this used to be S, okay, the equation relates to be S phi by rho. So when it comes to rho here, this is S phi. Okay, so this is the way we want to write the equation. Okay, once this is done, what I do is on the left hand side, I add a phi into del by del x of rho u plus del by del y of rho v, which is equal to 0 by continuity equation when rho is constant. Okay, so this is phi. Let me write the phi clearly. Okay, so if I add this to the left hand side, because this is 0, that doesn't change the equation. So I get this equation in the form of del by del x of rho u phi that I get from the left hand side, and the right hand side, if I take gamma as a constant and take it in, there is a minus gamma del phi by del x. Okay, so this is one part of the equation that I get, plus the other part of the equation is del by del y of rho v phi minus gamma. So if I call this as gamma x and gamma y, in order to allow these two values to be different, then it will be del phi by del y is equal to S5. This is the general form of the equation. So now if I take a control volume, okay, and let us say this is point P and this is the neighboring point capital E. I'll use a map notation to say east and west and north and south. Okay, so in 2D, there are 4 neighbors, east, west, north, south, and the control surfaces I'll write using the small letter and say that the velocity components are marked here. So let us say this is small e, small w, small n, and small s. Okay. Now this will be ue, uw with a small ue, small uw. So this is the way the equation is, the control volume is going to look. So if I integrate this with respect to x to x plus delta x and y to y plus delta y, where this is x and x plus delta x, this is y and y plus delta y. Okay, so basically you are integrating it from west to east and south to north. Okay. Let me rewrite that clearly so that it becomes visible properly. West to east and south to north, and this whole thing will be integrated with respect to dx dy, and this will be integral of these again, south to north and west to east of dx dy. Okay, so if I do the integration properly, since del by del x dx would get cancelled, so the delta y would get, if I assume the values are uniform over this small segment and this small segment because the total volume is very small, then I can take this rho u phi to be uniform over the west and the east, and similarly this rho v phi to be uniform over the south and the north. Then I'll be able to write rho u phi minus gamma del phi by del x, gamma x by del x multiplied by delta y from west to east. Okay, and similarly plus rho v phi minus gamma y del phi by del y from south to north to delta x. This will be the integral of this plus this, and that will be equal to S phi. If I take it as uniform in this region, this S phi is the representative value of this region multiplied by delta x delta y. Okay, so that is your integral. Now if I take this in, I'll get a rho u delta y multiplied by phi, the whole thing at east, minus similarly gamma east into del phi by del x. I can del phi by del x at east will be phi at capital E minus phi at capital P divided by this. If I use a certain differential scheme, phi E minus phi P divided by, if I call this as delta x on the eastern side, this is delta x E. Similarly, I can have delta x W, and this itself is delta x. So these need not be exactly equal; they can be different in different forms. So this is a form I can write. So this rho u delta y is nothing but the mass flow rate through this, because if I take it as 2D with unit depth, the area is delta y into 1, and velocity into density into velocity into area is the mass flow rate. So if I call this as Fe, and similarly this gamma E divided by this one, if I call it as dE, which is actually in some form a diffusion coefficient, then I get Fe phi E minus dE times phi E minus phi P. Okay, so that is one term. Similarly, I'll get a FW, phi W, dW, etc. So I'll be able to write this in the next slide as Fe phi E minus dE into phi E minus phi P. This is the first term, the east term, minus the west term is FW phi W. So this is a small w, okay, minus dW multiplied by phi P minus phi W. Now this is a capital W. This, what we are written here is capital. Similarly, plus Fn phi N minus dN times phi N minus phi P. Okay, so this is the northern term minus the southern term is Fs phi S minus ds into phi capital P minus phi capital S. So this is the left hand side, and that will be equal to the right hand side, which is S phi delta x delta. So now the phi E, phi N, phi W, and phi S are values of the values of phi in the control surfaces between the grid points. So if I look at the value here, so if the value of phi here is phi capital N, this is phi capital P and phi capital S, the value of phi here is phi small n and phi small s, which has to be obtained by interpolating these. So if I have computed the values of phi P and phi capital S, this phi small s will have to be obtained by interpolation between those two. Similarly, phi small n should be obtained by interpolation between these two, and so on. So these values have to be obtained by some form of interpolation by assuming a certain velocity or a certain phi profile between P and N, P and S, T and E, and P and W. This is quite similar to the finite element method, where you assume a certain shape function to obtain the values at the elemental faces. Okay, so if I have to do that, and then if I use an appropriate interpolation, so you to find phi E, phi W, phi N, and phi S need interpolation. And this interpolation itself will be determined by F and D, okay, in each direction, depending on which way now what are these F and D? F is the advective term and D is the diffusive term, as we have seen here. So the F is the advective term, rho u phi, so this is the m dot multiplied by phi. So this is the advective transport, and this is the diffusive transport, the diffusivity divided by the delta x multiplied by the difference. So this is the diffusive transport. So F by D gives the relative ratio, strength of this, which is normally called the Peckley number. So Fe by dE would be called Pe, which is the Peckley number, okay, which is the relative strength of the advection with respect to the diffusion. Okay, so depending on the values of the Peckley number, the interpolation is determined. If it is very strongly advective, then you take upstream differencing and so on. So if you use that and then obtain these, then this whole thing can be expressed in the form of AE into phi E minus phi P plus AW into phi W minus phi P plus AN into phi N minus phi P plus AS into phi S minus phi P plus Fe minus Fw plus Fn minus Fs multiplied by phi P is equal to S phi into delta x delta y. where this AE, AW, AN and AS are the effective coefficients of the phi E, phi W, phi N and phi S by using appropriate interpolation. So that will vary with the kind of interpolation that you used. Okay, and you will get the coefficient AP, which is the coefficient of phi P, will be equal to AE plus AW plus AN plus AS plus FE minus FW plus Fn minus Fs. Okay, so there should be a minus sign here. Okay, so and if continuity equation is correctly satisfied, this would eventually go to 0 in these equations. Okay, so this is the way this is defined. So if I use this, then I can say AP phi P is equal to, so if this, I can call it as B, okay, actually I should have gotten this whole thing with a negative sign, so then the sign convention is not a problem. It actually should have been phi P minus phi E, phi P minus phi W, phi P minus phi N, etc., and this should be plus. So then it becomes this. Okay, so AP phi P is equal to, then the other things go that side, AE phi E plus AW phi W plus AN phi N plus AS phi S plus B is the way the equation looks like. So this is an equation where all the coefficients are written in terms of this. So this is the way we derive equations, which are simultaneous linear equations of in adjacent values of phi, and you get a 5 diagonal matrix in the case of 2D and 7 diagonal matrix in the case of 3D, which needs to be solved in order to get all these phi values at all the grid points. Okay, so this is the method of solution. So going one step further on this, pressure correction. So the method that I just showed you is useful for solving for any equation. Okay, so if, for example, all the quantities that I require to calculate the AP, AE, AW, AN, AS and B are known to me, then this is a simple linear equation that I can solve for phi. So that can be the case, for example, for the energy equation once the velocities are all solved for, and the vorticity equation once the velocities are all solved for. But it is not the case for the momentum equations because they have mutual dependence, because AP, AE, AW would also be functions of unknowns, because also there is non-linearity, so there is need for iteration. Okay, so these equations, using this, you can actually solve for the variables. But for pressure correction, what you try to do is to write that if I go back to this, so if I want to write for this velocity, the velocity is actually between these two, a staggered velocity. So that AP for this eastern control volume for velocity would be in terms of the pressure at east and the pressure at point P. Okay, so if I write the x momentum equation, you will get AP UE, AP, if I AP for the eastern control volume, APE UE would be equal to summation over the neighbors of, let's call it as A neighbor, U neighbor, which is actually AE, AW, AN, AS corresponding to the UE, okay, plus the B term will actually contain the pressure. Let's expand that. So it is actually minus del P by del X. So it will contain PP minus PE divided by delta XE. Okay, so this is the term that it will contain. Okay, because your pressure equation yeah, so the S phi corresponding to the momentum equation, S phi corresponding to the momentum equation will be this rho would have gone the other side, so it will be minus del P by del X. So if I write it in terms of the derivative, then it will be P, this is PE minus PP with a negative sign, so it is PP minus PE multiplied by divided by delta X. Okay, so that is the term that I will get. Okay, so this is the expression that I would get. Now, similarly, Y momentum equation for the northern control volume. So if I take this as your control volume, this is P, this is E, and this is N. I can write for E and N. So there is the UE and VN. Okay, so this UE I have written the equation for. Similarly, I can write for UW in terms of PP and PW. Okay. Similarly, north I can write APN VN is equal to summation of over the neighbors of A and B, V and B. This A and B and this A and B not the same, but let's just say, okay, so let's get prime and B plus PN minus PP divided by, sorry, PP minus PN PP minus PN divided by delta YN. Okay, so now in the same way I can write APWUW is equal to summation over A neighbor U neighbor plus PW minus PP divided by delta XW. Okay, so similarly APSVS will be equal to summation neighbor of A and B prime, B and B prime. So these are different from this. Just writing to write the notations so that you get the form PS minus PP divided by delta YS. Now, if I write U is equal to U star plus U prime, and V is equal to V star plus V prime, and P is equal to P star plus P prime. Okay, so then if I substitute that into this becomes UE star plus UE prime. Okay, this becomes UNB star plus UNB prime, and this becomes PP minus PE plus, sorry, this is PP star plus P minus P star plus PP prime minus PE prime divided by delta X. Now in this, the starred form of the equation has already satisfied the momentum equation and therefore can be cancelled out. So I can cancel this, this and this, and that leaves a correction for prime. APUE prime, APE into UE prime is equal to summation over the neighbors of all the corrections plus this. Now, if I neglect this term, saying that eventually when it converges, this U and B's are going to go to 0. So let me not take into account the corrections of the neighboring points to affect the correction at any given point. So then this equation reduces to APE UE prime is equal to PP prime minus PE prime divided by delta X. Okay, so and when it is integrated, there will be a delta y here. That's the thing, and this is delta x here. So this will be a delta y by delta xe. So I can write ue prime is equal to ape delta xe divided by delta y. So this is something which I can get. Similarly, I can get an expression for uw prime, and similarly I can get an expression for vn prime and vs prime. And once I get this, I'll integrate the continuity equation. Okay, so what do I get? Integrating equation number 1, which is del u by del x plus del v by del y equal to 0 over the same control volume. I'll integrate this. I'll get ue minus uw divided by delta x into delta y. Okay, so this if I integral west to east and south to north, dx dy. Okay, so then what happens? Your delta x would actually go off, and you would get u v minus uw into delta y minus plus vn minus vs into delta x equal to 0. So if I write, then u is equal to u star plus u prime, and v is equal to v star plus v prime, then I'll get ue prime minus uw prime into delta y plus vn prime minus vs prime into delta x is equal to negative of ue star minus uw star delta y plus vn star minus vs star into delta x. So now this ue star, uw star have already been evaluated. So this is basically the difference between the left hand side and right hand side of the continuity equation, substituting the guessed or the recently calculated values of u and v. Okay, so that is the residual of the continuity equation, and as this reduces to 0, these also will reduce to 0 as they go. Now here for ue prime, uw prime, vn prime and vs prime, I substitute from the pressure corrections expression that I wrote here. So I'll get an equation. This leads to an equation in P prime of the form AP PP prime is equal to AE PE prime plus AW PW prime plus AN PN prime plus AS PS prime plus B. Okay, where this B would contain the residual of the continuity equation. So now this kind of an equation you would get at every point. Solve this to get P prime at all points. Okay, so the continuity equation leads you to a P prime equation which you can solve, and once you solve for P prime, then you can go back to these expressions which you have just derived, and using the values of P prime that you have got, you can actually get the values of U prime and V prime. Okay, so once those V prime, U prime values are available, then add that to the UV values. So using these expressions, you can actually correct the U star to U and V star to V, and similarly P is equal to P star plus P prime. Okay, so you can correct the pressure and velocity, and then you can go back to solving the momentum equations again. So I hope the pressure correction method has become clear to you. Okay, so what I will do now is to show you a few slides where I use this method to solve the boundary layer problem and obtain the solutions. In one of the future classes, I'll ask one of the TAs to demonstrate how to use the software so that we can also learn how to use the software. But at the moment, I'll just show you the presentation, which contains the slides which show some of the results that I've got. So this slide shows the computational domain that I have used. So computational domain is the region in the space which I am actually solving the equations for. So the boundaries of that would be, at the bottom I have the flat plate over which the flow is happening, and this is the leading edge of the flat plate at the left hand, which is x is equal to 0, and I have got a domain which is 30 centimeters long, so I have a plate which is 30 centimeters long, and in the vertical direction I have solved anywhere between 2.5 and 5 centimeters, so that the boundary layer thickness, of course, normally would be within a couple of centimeters at most, depending on what fluid and what Reynolds number that I am using. So I have used up to 5 centimeters here, and in some case, in the case of water, I have used up to 2.5 centimeters. Right? So that is the thing. And what I have tried to do is to discretize it in the form of a computational grid, which is shown here in this slide. So you can see that the domain is discretized into rectangular control volumes, and I have deliberately made the control volumes, number of control volumes near the boundary to be substantially larger in density. That is like a much smaller in size, and therefore many more control volumes clustered around there. So if I show you the next slide, which shows the close-up view of this corner of the grid, it shows something like this. So you can see that near the wall, the grid points are much closer, because that is where much of the gradients are going to be there, and far away from the plate, the gradients are going to vanish, and therefore the grid can be smaller, or grid can be larger. Okay. So the case that I have solved for first is the flat plate boundary layer with air as the working fluid, whose Prandtl number is 0.71, and the velocity and temperature of the free stream are 1 meter per second and 320 Kelvin, and the plate itself is at 300 Kelvin. So now with this and the plate length of 0.3 meters, the Reynolds number at the end of the plate comes to about 66,666, which is substantially in the laminar region. For flat plates, the flow becomes turbulent at Reynolds number, which is 10 to the power of 5 into 10 to the power of 5, and therefore we can comfortably work with this as a laminar flow. So the first slide shows the contours of constant velocity. So different colors indicate different velocities. So you can see here between 0 and 0.1 it is this dark blue, and then 0.1 to 0.2 is this color, and so on. So you can see that in this region, actually it's showing a velocity greater than 1. So there is some numerical error that is there in this solution. I'll just, so that's also responsible for all this wiggly and wavy. There's some numerical instability in the solution process, which I need to correct. But at least you can see that the thickness of the boundary layers, I have actually made the scale in the y direction 20 times the scale in the x direction. So if this looks like 5 centimeters while this is 30 centimeters, this is actually 5 divided by 20, which is 2.5 centimeters. Right, so that is the thickness of the boundary layer that I have. So the thickness of the boundary layer goes close to about 2 centimeters here, and the velocity reaches close to 1 at that location. Okay. So the next slide shows the contour of temperatures. So you can see the wall is at 300 Kelvin and the free stream is at 320 Kelvin. So every color block is 2 Kelvin change. So this is 300, 302, 304, etc. and this is the edge of the boundary layer where it goes close to 320. Okay, so the thickness of the boundary layer, again in this case the vertical direction is scaled up by a factor of 20. So if this looks like 5 centimeters, it is like 2.5 centimeters. So 30 centimeters is the length and 2.5 centimeters. So this I have just enlarged so as to show you. So the thickness of the boundary layer at the end of the plate goes to somewhere close to that, and you can also see that the velocity and temperature boundary layers, the previous slide and this slide, the thickness of the boundary layers are not enormously different. The thickness of the boundary layer is quite similar to each other. Okay. So you can see that the velocity is actually, because of the instability, it's actually going a little beyond 1. It should have actually been within 1.0. So it's going a little beyond 1 at different locations. That is inlet 5 centimeter, 10 centimeter, 15 centimeter. So this is the inlet, then this is 5, 10, 15, 20, 25, 30 centimeters. This is total of 30 centimeters. So at different locations, the velocity profile is basically showing the along. So at 5 centimeters, if I draw a vertical line, how does the velocity vary from here to here? That's what it's showing. So the velocity profile is at 5 centimeters this, 10 centimeters, 15, 20, 25. So you can see that as we go further in the boundary layer, the solutions are pretty close to 1, but here it's going, and that is why we are not able to see the thickness of the boundary layer very clearly here. But even then, we can see that the thickness of the boundary layer is not greater than 2 centimeters. This is a 2 centimeter mark, and this is 2.5 centimeter mark. So the thickness of the boundary layer is actually closing well within that. And thermal boundary layer also, you can see that the thickness of the boundary layer at the 5 centimeters is this, 10 centimeters, 15, 20, 25. So the thickness of the boundary layer is somewhere close to 1.3 centimeters at the end of the bowl plate. So that is the thing that I was actually trying to show you. In the other simulation that I have done, I have taken water as the working fluid. So Prandtl number of 7, the same boundary conditions. U infinity is 1 meter per second, and T infinity is 320 Kelvin, wall temperature is 300 Kelvin, and plate length of 0.3 meter. This gives a Reynolds number of 3 to the power of 5, which is still in the laminar region. So I have drawn the velocity contours. You can see that here it has not exceeded 1 by a great amount. It's still staying put. And you can see with the same magnification of 20, the boundary layers are much thinner, right? So if this is, let's say 2 or 2.5 centimeters, so you can see that this is well under the thickness of the boundary layer is just about 1 centimeter or less than that. And the thermal boundary layer is also of this kind of thickness. The thermal boundary layer is much thinner. Okay, so you can see that the velocity boundary layer is within something like, this is 4 millimeters. The thickness of the velocity boundary layer stays under 3.5 millimeters in the whole region, and similarly the thermal boundary layer also stays under 1.6, 1.8 millimeters in the whole region. Okay, so that is the result that I wanted to show you. Okay, we'll stop.